Okay, in this lesson we're going to be looking at more logarithms. We're going to be looking at how we can evaluate some more complicated looking logarithmic expressions using the inverse property. And the other part of this lesson, we're going to be learning how to graph logarithms and to compare how logarithm graphs relate to exponential function graphs. So let's look at the logarithmic function again. Remember, it's the inverse of the exponential function. That's a key concept here. We had y to the bx. We swap our x's and y's and solve for y. And this is where we need to use our logarithm. So we have these two functions here. Y is equal to b to the x. And we have our other function, log b of x. These are inverse functions of each other. And so I'll abbreviate. I'll give one the name e for the exponential function, the other one L for the logarithmic function. And based on the definition of inverses, I can, the composition test, it says that e of L of x is simply x. They undo each other. They kind of, in a sense, cancel each other out. L of e of x is equal to x itself. Whatever the exponential function does to it, the logarithm undoes it. So in this particular case, when I have b raised to the power of log b of x, I simply get back x itself. They undo each other. When I have log base b of b to the x, again, I don't want to say cancel exactly, but they do undo each other, and so I just get simply x as a result. So if I have an expression like this over here, it looks complicated, 5 to the power of log base 5 of 37, but it's actually rather simple because they are inverses of each other. 5 to the power of log 5 is going to be equal to 37, simply x. This is going to be 14. 10 to the log, and when we don't have anything written here, we can imply that it's a base 10. So these are inverse functions, so 56. We have our natural log, which is base e, so these are also inverse functions. We do need to make sure that the bases are the same here, e and e, 10 and 10, 3 and 3, 5 and 5. Over here, these are opposites, 2 and 2. We have a log and a power, so it's going to be 16. Log 7, 7 raised to. Opposites, these are opposites. This is our implied log base 10. We have the same bases, so we can apply our trick. These are the same bases here, log base e, natural log, e to the 13th power. This is going to be 13. So here's another example. In this case, the bases are not the same. So this is not equal to x. But we can convert it to the same base because 25 is 5 squared. We can write this as 5 to the 2x power. Now we do have inverse functions right here, so this is going to be equal to 2x itself. So try out these next problems. I'm going to continue though. Let's turn to graphing. Again, we have inverse functions. We know that inverse functions are a reflection of each other across the y is equal to x-axis. So we have here our exponential growth function. We have our exponential decay function. And the inverse of both of them will be reflections across the axis this y is equal to x-axis here. Now, a key concept is, in the case of the exponential function, we had a horizontal asymptote. Now we will have a vertical asymptote. The vertical asymptote for these graphs is going to be at x is equal to 0. This graph right here, the exponential graph, will get very, very close to 0, but it will never touch x is equal to 0. In terms of range and domain, it's going to be the opposite of the exponential function. If you recall, the domain for exponential functions were all real numbers, all the way across, and the y value was limited to only values greater than 0. So it's exactly the opposite with logarithm functions. Instead, the domain is restricted. We have our vertical asymptote, and so anything to the right of the asymptote, all the values of x greater than 0 are our domain, and then the range can swing from negative infinity all the way to positive infinity, so the y value consists of all the real numbers. Okay, let's graph a couple of these. We start off with graphing the asymptote. In this case, the asymptote will be at y is equal to 0. Now we're going to plot out a couple of points. To do this, I'm going to set values of y instead of values of x, because things are opposite and it's a little bit easier to think in terms of setting y values. So to figure out the x value, I think like this: 3 to the y power. So 3 to the 0 power is equal to 1. 3 to the first power is equal to 3. I plot these 2 points out, and then I can draw my logarithm graph. Remember, it hugs at the bottom here the asymptote, but it never quite touches it. Let's graph another one. Let's graph one with a fractional base. Same idea though, draw the asymptote at x equals 0. I'm going to set some values of 0 and 1 for the y value. 1/2 to the 0 is 1. 1/2 to the first power is 1/2. And I'll do one more point. Negative 1. 1/2 to the negative 1 is 2. And I can plot these 3 points out and then connect the dots for my graph. Okay, one more last example is the translation of the logarithmic graph. So in this case, we have this similar construct that you should hopefully be getting used to. The h value here shifts the log graph to the left or to the right. Then we have the k value. The plus k shifts the graph up and down by a value of k. Since we have a vertical asymptote, the vertical asymptote, which is up and down, is going to be moving to the right or to the left according to this h value right up there. So in this case, or our vertical asymptote will be at x is equal to h, and in this particular case, h is negative 3. So we draw our asymptote at x is equal to negative 3. So this is different than the exponential graph, right? For the exponential graph, we looked at this k value because the horizontal asymptote moved up or down because of the k value. In the case of a logarithm graph, moving a vertical asymptote up or down by k doesn't do anything to it. But the h value moves it left or right. In this case, again, x plus 3, our shift in the horizontal direction is 3 to the left. So that's where our vertical asymptote will be. Now, finding 2 points. This is a little bit trickier. What I'm going to do is I'm going to take this function and I'm going to subtract 1 from both sides. And so I get y minus 1 is log 2 to the x plus 3. Then I'm going to convert this to exponential form. I'm going to say 2 to the y minus 1 power is equal to x plus 3. I'm going to use this equation right here to calculate some points. And hopefully you'll see why this is a little bit easier. Now I'm going to choose some values of y that will make this easy to evaluate. So when y is equal to 1, it's very easy. Also 2 is not too bad either. So let's plug these values of y into this equation and solve for x. So plugging in the 1 into the equation, I get x is equal to negative 2. Plugging in 2 into the equation, I get x is equal to negative 1. I plot these 2 points out, and then I can graph my logarithm function. Now, let's finish off with talking about the domain and range. In terms of the domain, we have our vertical asymptote here. So the x values are only values greater than negative 3. And for the range, we have values of the y that go from negative infinity to positive infinity. So all real numbers is the range for this function here. So that's how we graph it. You can try this last one on your own. Try graphing this out. We'll be doing this in class as well.